it's about time to get started. So, is the sound on? I'm not sure. Yep. So hello, this is Junichi Horikawa, and this is the 33rd episode for Houdini Tutorial Live. And this is the weekly tutorial live that I'm doing in order to create some algorithmic design stuff using Houdini. Alright, and the topic today that I would like to try to implement is a Mobius transformation in 3D. And here is the result, what I get using a three-dimensional Mobius transformation, and I am using one of the code written from the other guy, which was on the gist, so I'm gonna show you that as well. So it's going to be pretty easy. I'm just going to copy paste the code, the existing code, and try to modify it so that you can use it in Houdini. Right, and using it, you can use this for any kind of geometry like texts or simple geometry like these. It can also be applied for wireframes or just the planes and so on. Okay, now first of all, let me show where I have referenced the code and the idea from. So this is the web page, a blog written by a guy called Daniel Piker, a developer of a kangaroo physics engines for Grasshopper, and he has been writing a lot of interesting articles based on geometries and physics. And one of the articles, which was written in like 2008, is this one, a Mobius Transformations in 3D. And he has implemented this by using a inverse geographic projection together with the 4D rotation, which I have also tried some time ago using a box. And he also reproject the 4D rotated object into a 3D space by using a geographic projection again to create this kind of interesting effect, this interesting morphing geometry. And he has posted the code on the gist, where you can copy and paste to use for any kind of softwares. So I have brought this up into Houdini to see if I can use this in Houdini as well. I think it is basically written for a Rhino and Grasshopper, but it worked just fine in Houdini. So I'm gonna show you how you can do that, which is going to be pretty easy. And I don't think it's going to take much time to do this. Okay, so what you really need is just some geometry that you want to transform. So let's just give some geometry and create some geometry that you want to transform. Maybe you can test out with some test geometry. So choose one of the geometry you want to deform, probably using like let me see, squab. Might be great because he has a lot of details. Could be interesting. Now, what we can do now is to directly go into the code which Daniel Piker has written, which was this one. So I'm just going to copy all these lines and use this with a vex and transfer this to a vex code so that I can use it in Houdini. So I'm gonna copy this and use a point wrangle so that I can control each point. Now the position where squab is placed is important. Basically the Mobius transformation works like transforming the plane into a sphere and sphere into a plane. So maybe it might be good to start with the grid to show that the grid becomes sphere and becomes plane again, back to plane again. Okay, so I'm going to create a plane like this and create a point wrangle, and I have just copied paste the code from Daniel Piker's gist code. Now the first one determines the working plane, which plane I should be working on. Now let's just say I'm working on XY plane, XZ plane, so I'm just going to remove that because I can control that with other node in Houdini, this one as well. Okay, so PT currently right here it is the position, I think, so this can be expressed by at P, but at this point I don't really want to update the position yet, so I'm going to copy the positions to a pos variable. Okay, and then next I have some parameters right here. It's a radius for the circle, so maybe I can create some channels for this, named as radius. Okay, now the PT is equal to pos, so I'm going to replace these PT to pos, and I'm going to replace double to float. And all these doubles to float. Okay, now first thing it's doing is retrieving the X, Y, and Z coordinate for the positions. I think I have to make it lowercase. And first transformation is the reverse strographic projection to hypersphere. So it is projecting a plane into a sphere using a inverse strographic projection. So which is, if you search the strographic projection in Wikipedia, you can see that the strographic projection is a projected shadow of a geometry or points on a sphere. So say the light is at the top of the sphere, then you project some rays to some point on a sphere, then that shadow is the projected plane. So this is this strographic projection works to transform the geometry on the sphere into a plane. Now, using inverse strographic projection means to give this plane back to a sphere. That's what it's doing right here, and it also has a full dimensions right here. That is because Daniel Piker is using 4D rotation afterwards to rotate the projected point information, to rotate it in 4D, then project it back into 3D. Okay, so let's say what else I have to change. These lines looks okay. Now these lines, for the math dot cosine, I can just replace with underscore cosine underscore sine, like these. This. Okay, and I have this, we have this parameter t to rotate hypersphere by amount of t, and the t can be in range between 0 to 2 pi to create the rotation in this case. So let's create a t as a parameter. I'm going to create a t as a parameter, as a float. Now what else? These looks okay. Maybe I should make this float just in case. And right here it's creating a new point position. So let's create the p using vector instead of point 3D, and using set. And last of all, it's multiplying with the radius again, right, with this one. So maybe I should give a radius the name with some variables. So float rad is equal to chf rad, then divide the current position by radius, and then on the end we can multiply back with the radius. Okay, so currently no errors, and rebuild this. Now let's set the range for radius and t. Now the radius could be in between 0 to 1. I think that's fine, but maybe let's try to increase this to 5 for the maximum. And then for the t, this could be in between 0 to pi multiplied by 2. So well, I'll just keep this by 0 to 1. Then I am going to multiply this inside the code by pi multiplied by 2, so that if the t goes to 1, then you'll get a value 2 multiplied by pi, which is 360 degrees. So let's see what would happen. Now nothing happens. That is because I didn't update the current point positions with this p. Okay, something happened. Now, okay, now it is rotated, but it seems like it's rotated in 2D, like this. So that is because I think the code was written in cat based orientation, so that means the upper dimension is, upper axis is z, but in Houdini the upper axis is y, so I think we gotta replace y and z in this case. So let's do that. So right here should be fine, right here these should be fine, doesn't really make any changes. Okay, so I think these are the places that I have to change doing the 4D rotation. Okay, so let's replace this y with z. Okay, so z here, z here, z here. Okay, and replace z with y. So this one goes with y, this one goes with y, and this one goes with y. Okay, now I think I need to, this one should be okay. Now let's see how it goes. Right now, the Mobius transformation has been successfully transferred from Rhino to Houdini. Looks good. Now I can animate this by using like frame-based values like frame divided by the frame end, which will give you a value in between 0 to 1 using the first frame, starting frame to the end frame. Let's set the end frame to 100. Okay, pretty easy. Now let's try to use this with this squab geometry, how it's going to be look like. And something really uncomfortable happens. Yup. And you can try to see the effect of this transformation by transforming this geometry itself with other angle. Like, let me bring this to somewhere around here with the t value, and say if I move this back and forth to the y direction, we'll change like this. To the x direction, we'll create something interesting. Well, the right hand becomes really massive. Now what if I play with this one? Yeah. That's pretty disturbing but interesting. Right. So, I mean, that's pretty much it, what you can do with it. It's just about playing out with this code that I have transferred using together with a different kind of geometry. Maybe what I would try is to place this squad on a plane and see the difference between the geometries in different places. So let's use copy 2 points and place this squad into a grid, onto a grid. Okay, that's too much. Now let's lay this down. To 90 degrees. Oh, not this one. Okay, I think I have to bring this back to 0. Okay, not like this. Okay, well, let me just place this into z plane. Well, currently it is. Is it? Well, I didn't want it to rotate this. Okay. Now I wanted to rotate this one instead to 90 degrees. Maybe to 45 degrees on y-axis, maybe z-axis. Okay. Okay, and let's try this one with a Mobius transformation to see what would happen. And if I play it, okay, well, where does this plane placed? Where is where does this... Okay, I think it's not centered. Let me see why. Okay, I have this transformation. Okay, now let's try. So you have... I don't know how to explain. You have something like a ring-like grid made with a squab. Alright, wow. So, I mean, you can do a lot of stuff with this Mobius transformation, a lot of experiments using this Mobius transformations. One that I found beautiful is just using a simple geometry, like primitive geometry, like cube, together with a sphere. And for a sphere, I'm going to convert it into a polygon with some high frequency and do the Boolean difference between these two. And probably do a remesh after this. And oh, hello Gravella, thank you for the super chat. And if I do with this kind of simple geometry, the result that I get is pretty interesting. It's rather simple, but it gives you really beautiful transformations. Okay, well, let's set this target size a bit smaller. And you can also try to change the radius right here to change the overall projected size. Maybe it's better, it might be better, you can see the result better with the grid, what the radius does. It just changes the projection sphere, size of the projection sphere. So let's set it to 50 by 50. And if I raise up, let's look at somewhere right here, and if I raise up the radius, it's just give you the big sphere as a target. So more radius you have, the closer you get as a plane. Okay, that's just it. Now, after you have implemented, I guess what you can do is to play around with some of the parameter right here, some of the equations being written right here, by trying to tweak some of these equations to see what would happen. For example, like for the W value, when you do the 4D rotation, if you change the T value to see what happened, you would start to see some kind of a twisted rotation. Interesting. So also try this out for the Y. If I multiply by 0.5, some transformation that I no longer can guess what would happen next. Which could be interesting, but I don't know how you can control this as a visuals. Well, it's really up to you. The base code is, as I said before, is from a Daniel Piker's code on a gist, so keep that in mind. And if you are going to share the code, I think you want to mention who wrote the code. So this is the guide. He has made a lot of great stuff for the Grasshopper community, so right, so I guess that's pretty much it. That was really fast, but yeah, this week's is too really fast, but that's the things that I wanted to show you today. And I don't think I'm having much questions today, so I would like to end the live at this point. If no questions, there's no questions. I just wanted to show you that you can bring this interesting Mobius transformation into Houdini pretty easily by using a template code which has been shared to us. Okay, so that's pretty much it. You can download the files from the GitHub repository link on a YouTube video description if you're interested. And well, I would like to do another tutorial live next week as well. If you're interested, please consider joining. Right, so that's it. Thank you, and I'll see you next week.